So I've been at Cloudera for a little over a year in the product development department, but I feel like what I'm doing nowadays and what I've done for the last several years is a continuation of. No problem. Yeah, try this again. Give this a shot. Testing. Oh, excellent. But in a sense, I feel like it's good, yeah. So in a sense, I feel like I've been doing the same types of things for the last, this spring will make 8 years. So I joined the quant finance world in 2007 and found myself basically doing SQL programming and using Excel, and wasn't really happy with my own productivity, and found this Python programming language, and I guess the rest is history. Found that I really enjoyed creating data tools, and have proceeded to do that ever since. So I expect that I'll continue to do so for the next several years at least. So I am a big fan of Python. I think a lot of people do think of me as being somebody who's like ideologically a Python person, and Python to the exclusion of other languages. But I think I was really attracted to Python and have invested a lot in it because I feel it's a really good way to put software in the hands of users, and for it to be accessible, easier. It's gotten easier, but it didn't used to be as easy to deploy in production. But it's a good choice for creating well-rounded teams of scientists, engineers, and business people who can all use a common programming language to interact with data. So you can build production software, you can do interactive analysis. And I think when I initially started working with Python, I didn't know whether or not it was going to be successful, because I was working with a lot of economists and financial folks who weren't computer scientists, and so the challenge was to craft a tool set that could be accepted by a diverse group of non-software engineers. So Python was a good choice for that. But in the last 6-7 years, Python has become incredibly popular for data science, and I imagine that's why you're all here early on a Sunday morning to listen to me, so I probably don't need to tell you about this. And we have a lot nicer things than we did 6-7 years ago for libraries to handle all the spectrum of data wrangling challenges and machine learning and data visualization and so forth. I would say one of the biggest problems that Python programmers face, and what a lot of people come to me and they say, Wes, like, we really love pandas, but we want to keep using pandas. We want it to work with big data, and it's a hard problem because you have an entire ecosystem of tools which is created under the assumption that you have a data set in memory on your local machine. So that might be your laptop. So nowadays you can get a MacBook Pro with 16 gigs of RAM, so you can work with quite a bit of data on your laptop. But now you can get machines on EC2 with 2 terabytes of RAM, and so the definition of single node analysis has expanded to be quite large data. But if you do have big data, often you build a workflow that involves aggregating or sampling the data so that it can fit on a single machine, so that you can use the Python data stack. And so there's been like kind of a chicken and egg problem in that if you look at the right side of if you think about, if you want to, not that I'm into creating dichotomies, but if you're going to create dichotomies around data processing tools, I tend to think about the world as falling into the scientific computing bucket, which is a lot of data science. It's about doing computations, fitting machine learning models, doing statistics, and working with large array data. And that, of course, scientific computing is the reason why we have nice things in Python to begin with. that back in the mid to late 90s, scientists who were interested in open source started creating tools to wrap all of the legacy Fortran and C++ code in Python so that they could script legacy systems with Python code. But in the last 5 to 10 years, the way that when people say big data, at least in Silicon Valley, they're generally talking about stuff on the left side of the page. The data tends to be JSON-like, and increasingly with web technology, it's become very popular, or almost like the de facto standard, to just have all of your applications throwing off JSON data. All the JSON will go into the same pipe. It gets landed in S3 or some file system, and then you're left to wrangle the data into a form where you can analyze it. And so the tools for handling analytics data in the industry have developed separately from the scientific computing stack. And in general, the Python community has been investing heavily over on the right side and less so on the left side. And so if you think about what is pandas really, it's an effort to bridge the gap between Python scientific computing tools and industry analytics problems. So SQL programming, relational databases, statistical computing tools like R, which have built-in tables and things like that. So it was an effort to create an analytics industry domain-specific analytics stack using, to the best of my ability, the scientific computing tools in Python. And so the modern pandas project, which now is like 200,000 lines of code, in Python and Python and lots of different things with lots of submodules tackling many different problems. So we kind of had to create a whole walled garden ecosystem. We had to write our own CSV parsers. We had to implement all of our joins and table operations. Basically, you can think of pandas as being kind of like a sort of an imperfect in-memory database. And a lot of people do use it like an in-memory database. We had to add data types to account for limitations in NumPy. We had to implement our own representation of missing data, and as a result, there's a lot of technical debt that has built up in pandas. Not in a way that affects a lot of users, but thinking about how to kind of make the next leap forward into large-scale, distributed data sets from a pandas perspective. We can get a lot of the way there, but it's a very hard problem to make pandas magically big data enabled. So I do want to say a brief thing about pandas, and so many of you may know that there is, and many of you may not, that there is a nonprofit governance organization that we created in the Python community in the last in 2012 called NumFocus, and pandas just received its first donation of funds for development via the NumFocus organization. So it used to be there was a lot of questions around how do we enable companies to give money in a way that is through like a nonprofit organization to fund development of open source tools, and the NumFocus organization is helping do that for projects like pandas. So if you or your company want to help fund the development of these projects, that's a very good way to to get involved, is by contributing dollars to help support the open source developers. So meanwhile, in big data land, there are many systems for executing SQL, and many of these systems have evolved to be able to handle more and more complex data, and in particular, to be able to handle JSON data, coming off of web applications. So things like Google's BigQuery, Google's been analyzing big data in JSON-like format, probably since the late 90s, whatever it is, as soon as Google existed. Some of these other databases, it's not an exhaustive list, like Redshift, still has flat data, but may have nested JSON data in the future. But there's like a general trend happening in data science tools that I'll talk about in this talk. And that if you think about what is a SQL engine and what is the SQL programming language, so the SQL language is a way to describe computation. So there's no notion of parallelism, of data locality. There's really not that much information about the details of how a SQL query gets executed, and it's the job of databases to take the SQL and convert it into a physical query plan consisting of relational algebra, data transformations, and so forth. And so what's happening over time, and if you think about big data and Hadoop, was largely about decoupling storage and compute. So put all of the data in a distributed file system and then enable other systems which do compute only to read data from that distributed file system. And the same is true of things like Amazon S3. So you have a giant blob, giant bucket where you can put infinite data, and then you can have many different applications reading data from that distributed file system, and you might be executing SQL, or maybe you're running MapReduce jobs. Now increasingly, you're seeing a lot more Spark jobs, but it's nice that you can deal with storage in an isolated way and have multiple compute systems reading from those storage buckets. But the UI layer has gotten less love, and that's a lot of what this talk is about. And so if you think about big data architectures, imagine data, let's say you're using something like Slack, and so everyone around the world is chatting on Slack, and every time that somebody sends a message, all those messages go in through a streaming ingest layer, which is probably nowadays Apache Kafka. All that data, well, it gets distributed and sent out to all of the consumers of that data so that you see somebody's chat message immediately. But you can bet that every chat message which is sent into Slack is all recorded in a central location with all of the events and chat, basically Slack events that are happening all over the world for analytics purposes. And so typically, raw data gets stored in JSON, and then you have some kind of data transformation job for converting, cleaning and separating out the data that you're interested in, and converting it into some data format which is designed for analytics. And then increasingly, JSON data is converted into an efficient columnar table storage format, and then that data is queried with an analytic SQL engine, like a Presto or Redshift or Impala or something like that. And so if you think about Python is largely happening around in this part, this area. So you can write Python jobs to transform the data, but you're usually doing so at the expense of performance or scalability. Your jobs might run out of memory more easily if they're written in Python as opposed to Scala or Java. But Python's very active here, where you write SQL queries and then you do downstream data analysis in Python from the results coming out of analytic SQL systems. And one of the nice things about developments going on in analytic SQL is that a major trend is toward being able to analyze JSON directly in place without having to transform and normalize it. It used to be you would take your JSON, identify the relational schema that's embedded in the JSON documents, and then you would have a job which unravels the documents and puts the data into a star schema in a standard kind of DBA-approved relational database scheme. But now with things like BigQuery and Presto and Impala and Apache Drill and all these things, Spark SQL, you can reference a JSON dataset directly and run SQL queries on it that know about JSON types without having to go through that transformation step, which is really a productivity benefit. So when I got to Cloudera, I sat down with the team and said, how can we start to build a better Python big data experience? And Ibis, my new project, is an effort to build tools that work toward that goal. And so the two areas where I've been investing, the first is the SQL. So the SQL problem. Not that it's really a problem, but having to switch between writing pandas-like Python code and writing large SQL queries is it's a very different way of working with the data. It also makes it harder to reuse your code, to compose and create very complex queries, like refactoring SQL. It's easy to refactor Python, pandas code. It's very hard to refactor large SQL queries. So you would like to make doing big data analytics in Python, as composable, reusable, and easy to develop and maintain as possible. And the second is being able to extend big data compute systems with Python code and have it perform well, which turns out to be the harder problem in this equation. So I'm short on time, so I'll have to direct you to the pandas or the Ibis blog to learn more about the SQL DSL. But the idea is that what I tried to do was to craft a Python API for describing analytics, all in Python code that is feature complete with SQL. So if you have some SQL select query, but there's an equivalent way you can write that query using Ibis expressions. And the goal was to make the workflow and the API as similar to pandas as possible. And that's definitely inspired by people asking me, like, how can I work in a pandas-like way and have it work with big data? So the way that the toolchain works is you use the Ibis API. That's your user interface layer, and Ibis translates the expressions into SQL or other forms that are compatible with for the Hadoop architecture, whether that's SQL or could use Spark in the future. But right now it's focused on translating Python to SQL. There's support for SQLite right now. Somebody just opened a pull request for Postgres, which also enables Vertica, Redshift, and other Postgres forks. So if you have if you use a Postgres variant like Vertica or Redshift for big data, that might be an opportunity for you to hack on the project to add more support for those database systems. So I'm very keen to support as much of analytics SQL as possible, and to have the code be uniform based on, in some sense, like the promise of SQL was to have a standard query language and be able to switch out your database, but in practice, database dialects are different. They have different built-in function names, and so when you switch from one database to another, you have to learn a whole set of different function names for string manipulation and math and all that stuff. The idea with Ibis is to make everything, to have the same Python function call map onto the appropriate database function depending on your backend. So I don't have time for a demo today, sadly. So So the exciting part of Ibis is that because I sit right next to the Impala team at Cloudera, is that I've been able to influence Impala's roadmap in ways that are beneficial to Python and the data science community in general. And so the first thing is being able to to integrate with nested complex type support, which is just shipping in Impala and has been present in other SQL variants. So we'll support those as well. But the big thing, and I'll talk about for the next 10 minutes or so, is how to extend a big data analytic SQL system with Python code and achieve good performance. Later on, I'm very interested in doing more with the LLVM compiler translator toolchain to be able to generate native code from Python. But one of the issues with the LLVM translation compiler tools is that if you want to use your existing Python libraries and existing Python data stack in that environment, not everything can be compiled. So if you want to use parts of scikit-learn or parts of NumPy, that can't be in general. It can't be translated to LLVM IR. So if you think about the decoupling diagram, in a sense, Python lives in the UI layer, and the reason that Python is successful in data science is because the user interface that you have is so strong, is how can we have Python code execute in the compute layer. So the way it's hard is the summary, how to do this, because compute engines largely are not written in Python, and that's unlikely to change in a major way. So if you want to have Python code execute inside these systems, you have to have what I call an external language protocol. So this might be called UDFs, so like user-defined functions. And so the blanket term I'll use for it is external UDFs. So recently, Amazon Redshift got Python UDFs, and so they have to work through this external protocol. So Python is not running embedded inside the system. Python is external to the compute system, and data is being moved into the Python process to invoke the function that you wrote. So the problem with these external user-defined functions is that they're slow. And there are several reasons for that. So the first is that moving data into Python is expensive. And so that's typically called serialization overhead. So I'll talk about that in a second. The two other issues is that databases and big data systems in general are oriented at applying functions on one data value at a time. And as you all know, in Python, you want to write vectorized code that works on one array or one table at a time. So anytime you've ever written like a pandas function, which goes row by row, you'll know that that's incredibly slow. And you can. The other thing, which I don't have time to talk about, is the cost of invoking external Python code through like a Unix socket or something like that. But just vectorization, just to give you an idea of the performance the performance impact of vectorization. So this is a SQL statement with like an if then else with two arrays and then summing the result of adding those two arrays together. So I ran a benchmark, and the green line is the pure Python code at 1. And by writing naive NumPy vectorized expressions with temporary variables, that's the blue line. The red line is writing a Cython function. The purple line is an optimized Cython function. And the y-axis here, I should work on the labels. The middle line is 100 times speed up, and this top line is 200 times speed up. So by being careful about writing vectorized compiled code, with Cython or using NumPy, you can get anywhere from 50 to 150 times speed up, and that can be even greater through better code generation. There's been instances where Numba, the LLVM compiler, has seen 1,000 times speed up over interpreted Python code. So you need to be working one array at a time. So the solution, and it's a hard problem to solve, is having an interface to big data systems which is vectorized, so it hands off data to Python one chunk, one array at a time, so that you get the vectorized performance benefits. But you also have to have a memory representation that doesn't require conversion on both sides. So the current state of affairs is that you have your master system, you convert data to a form that Python can read. Python pays the cost to convert that into its own data structures, like NumPy arrays, pandas data frames. You run your computation, and then you write back the results into a form that the host system can read. So the only way you can make that, and that's the biggest cost, it turns out, is moving data between the systems. And the only way to solve that is to have a shared memory representation. So what we were doing, and it's already been done in the Apache drill project, they created a table, a columnar data representation that can be used for external code. The same thing is happening in Impala. The idea is to have a set of data structures which are the same on both sides of the wall, so you can have basically move data into Python without any conversion at all. I was going to talk about serialization, but I don't think I have time for that. I'll say a couple words. So there's an effort underway to create, we're at the specification stage, a standard set of table data structures, not even table data structures, they're array data structures that can handle the JSON type system, if you think of it like that. That can be the same both on the analytic SQL side as well as the Python, R, Julia side. We'll create a standard reference implementation in probably C++ that we can wrap in Python and all the data science languages, and that will create a shared set of tools that can be available to all of the data science users, and then interoperate with any system which speaks that protocol. And some people have asked me how this effort differs from serialization formats, things like the Apache Parquet project, which you might be familiar with. And so the thing about columnar storage is that there's an explicit trade-off for space efficiency for CPU deserialization. So if you strike the right balance between how fast can you stream data off of spinning disk hard drives, and how quickly can you decode, decompress, blow it up into fully materialized data structures. So things like Parquet, which was inspired by Google's internal columnar format, there's definitely there's the right balance there where you can decompress and decode data a lot faster than you can get it out of a distributed file system. And so the idea with this data structures effort is that it's an in-memory, fully materialized, kind of think of it as like you think about what's inside a pandas data frame. So it would be like new internals that could go inside like a pandas data frame that could also handle embedded maps and arrays and unions and so forth. So all of the things that you need to deal with nested JSON data. So if this whole effort of creating shared memory representations is interesting to you, it's I know it's kind of esoteric because as users of data science tools, you don't really see what's inside them very much. Not a lot of people know the internals of pandas data frames, so you only really see the API. So in a sense, this effort will be completely hidden from the user base, and the only thing will be you'll have a way to write code that is vectorized and fast that you can develop locally, and then if you need to use that in conjunction with Spark or Impala or some other big data system, you'll have a straightforward way of saying, I want to run this inside this distributed cluster, and it will perform in a reasonable way. So that's what I'm up to right now. I think my goal for the data science community is to enable Python to be an available and reasonable choice for working with data at any scale, and being able to leverage the existing ecosystem of packages without having to, obviously when you're working in a distributed setting, you do have to modify the way that you're thinking about describing algorithms on the data, but you'd like to be able to use the existing stack of tools as much as possible without paying a heavy performance cost to choose Python over other languages. So I think choices are good. Right now, choosing Python, it's been sad to see that that Python is not as much of a big data citizen for a good big data citizen for data science. So hopefully, within a few years, we'll be at a point where Python is just as reasonable a choice as Scala or Java or tools that have been developed for big data and Hadoop. So thank you. I think I might have a couple minutes for questions, maybe. Yeah, maybe like 2 questions. Sure.
What difference do you see between Ibis and Blaze?
So the question was the differences between Ibis and Blaze. Architecturally, there's a lot of similarity in that you have a Python DSL API and then a translator compiler subsystem. So there's that architectural overlap, but Ibis is really developed with focus on SQL compatibility, and so like wrapping all the built-in functions in a database and capturing all of the, being able to port select queries without any loss in functionality to Python has been like the goal from day one with Ibis, whereas Blaze is more focused on having a general data DSL that can compile to many different targets, including non-SQL targets. So it turns out that fully supporting SQL and like the relational algebra semantics affects the design of your DSL in like non-trivial ways. Another question.
So the columnar data structure is useful, like when the data is on the desk and the one is use columns, right? But when the data is in memory, like why do we need columns?
Well, so when the data's in memory, you still want columnar data structures because you're usually working on one column at a time, or in pandas you'll say like data frame, group by, column name, and so if you look at how the algorithm breaks down, there's a lot of places in the code where it's like scanning all the data in one column in one shot. And so anytime you're having like a scan down one column of a table, you're going to get major performance benefit from having all the data contiguous in one memory buffer.
But random access memory, right? So like it's much the efficiency involved with time much of the depth, right? So if you have random access memory, so you can access memory randomly. That's the advantage of random.
Well, I think so. I think what you run into is cache efficiency. So if you look at Stride, performance gains from contiguous versus strided memory access, you have the same thing with tables and columnar data. So, yeah. All right, thanks everyone.